Thank you, Nahil. And first, let me say thanks to everybody for a great meeting. I didn't quite know what to expect when I was invited to come here, and I know when I've gone to biological things in the past, I haven't understood anything. And this one's been very, very instructive for me, and I think the organizers did a great job in keeping sort of indentation as a theme, or at least contact and those kinds of things as a theme. And so it's been very useful for me to learn some things about biology in ways that about half of them make sense to me. So the second talk, I was asked to give two titles, and the talk title is Case Studies in Nanoindentation, the World of Soft and Biological Materials. And I need to preface this by saying that I don't work so much in that world. And I'm going to talk about what I think are some soft materials. Some of it is my work. A lot of it is other people's work. But many of these things you're going to say, that's not soft materials, that's hard materials, okay? So let me get that across first. And then secondly, I've realized by being at the meeting here, and now that I understand what's going on, that there's probably need for me to go back and continue the talk that I started yesterday, and I didn't quite finish, because there's a piece of that I've seen in many of the talks here that I don't think has been discussed in great detail. And I want to go back and start off and spend 10 minutes continuing my talk, which is this Nanoindentation 101 course. And specifically, I want to go down to this item right here. Last time we did hardness and modulus. I want to get to storage modulus and loss modulus, because there's been a lot said about that, and that clearly is of great interest in the biological world. A lot of you are using the basic principles that are here and understand them well, but I think there are some people that don't. And so I'm going to do a Nano 101 talk on storage and loss modulus. So this is a technique that Warren Oliver and I proposed back. It was actually in the appendix of that 1992 paper. So if you want to find this, a lot of people don't realize we did this back in 1992. It's in the appendix. So that's a long paper. You've got to go to the very end to find this. And so this was proposing what we called, what I like to call dynamic stiffness measurement as a technique that can be accomplished with nanoindenters. And the basic idea then is this, that in a normal nanoindentation experiment, what we do is we load up and then we unload. So a load time history looks something like that. But there's an alternative technique that's implemented with things called phase lock amplifiers or Lockein amplifiers, and many of you know what those things are, which becomes a dynamic measurement. And essentially what you're doing in this technique is that as you're increasing the load in a linear way, you put a small oscillating sinusoidal signal on top of the load signal. And you monitor the displacement signal at the same frequency. And that's what's done with these phase lock amplifiers or Lockein amplifiers. And if you then have the ability to measure, to know what the magnitude of the oscillation is in the force, and you can measure the amplitude of the oscillation in the displacement, and look for the phase shift of those two signals, then you have ways to do some things that you don't do with a normal nanoindenter. And so we implemented that back in this paper. Now, in order to do this, and this is one thing that a lot of people don't appreciate. We've been talking in here about maybe putting some things on websites that tell people problems that you can fall into, and people are ignoring, they're just using these things as black boxes and so on. And if I don't get anything else across to you today, it's that this is a technique that is extremely valuable. But in order to implement it and measure properties in a reasonable way and in a semi-accurate way, you have to very carefully characterize the dynamics of the machine in addition to the dynamics of the specimen, because if you don't get the machine dynamics factored out properly, you'll come to all the wrong conclusions and you'll get crap. The data, you'll go ahead and publish it because you won't know what happened to you, but it will be wrong. So understanding your machine dynamics is extremely important. I would also point out that this technique on the what is now Agilent, was MTS, and it started off as Nano Instruments machines. It's called continuous stiffness measurement, and it's a very, very valuable measurement technique. Okay, so the idea is something like this. Many of you know this, that what we're going to do is we're going to impose this small sinusoidal oscillation on the force, and we're going to measure the oscillation in the displacement. And what happens there then depends on whether the material is elastic or the material is viscoelastic. And essentially what happens then, if the material is elastic, is that the displacement oscillation is exactly in phase with the load oscillation, and you get a response that looks something like that. If the material is viscoelastic, then there's some damping in the material, there's some energy absorption in the material, and the displacement signal is phase shifted relative to the load signal. And you use a device called a Lockein Amplifier, which was developed specifically to measure these things. What happens in the Lockein amplifiers that we use is that the force signal is prescribed, the force oscillation is prescribed by the Lockein amplifier. The Lockein amplifier then picks up the displacement signal and looks to see what the amplitude of the displacement signal is and what the phase shift of the displacement signal is. So the basic measurements with the Lockein amplifier then are the force amplitude, which is input, the displacement amplitude, which is then measured, and the phase shift between the two signals, which is then measured by the Lockein amplifier. And if you can do that, and then you can measure two parameters that become important in the analysis. One I'm going to call the contact stiffness, and the other one I'm going to call the contact damping. These are properties of the material, but in order to get the material properties out, you have to subtract out the machine effects that are also measured when you're making these measurements. And to do that, you have to calibrate your machines to determine things like the spring stiffness of the machine, the mass of the machine, and the natural damping of the machine. There's a lot of damping in most nano indenters because they've got parallel plate capacitors in there that are measuring displacement, and they operate in air, and as these things move up and down a little bit, you've got to move that air around, and so there's a huge damping force that's created by the motion of that air in the parallel plate capacitor. And those things then have a marked effect then on what you then measure as the contact stiffness. To get the contact stiffness out, you have to take the measured parameters that come out of the Lockein amplifier and subtract off all of the machine components that are also contributing to that. And the same thing happens then with the contact damping. And very frequently, you find out that the stiffness of the machine, depending on what you're measuring, the stiffness or the damping of the machine may be greater than the stiffness or the damping of the specimen. And under those circumstances, you're subtracting big numbers from big numbers, and you end up with little bitty things left over, and you may have problems in the accuracy with which you're measuring those things. But if you get the machine constants out, then what is normally done is to assume that the material is behaving as a void solid through a simple viscoelastic analysis. So this is now the material response. And if you take these things right here, you can relate the storage modulus of the contact or the material to the measured contact stiffness corrected for machine constants. You can measure the loss modulus by taking the contact damping, C sub C times omega, and converting that via these parameters into the loss modulus for the material. The other thing that's frequently done then is to look at the tangent of the phase shift, which is then the ratio of the loss modulus to the storage modulus, or C sub C omega divided by S. Yeah.
How do you find those numbers for the calibration of the machine?
Most machines, or at least the machines we use, have internal procedures that you run to find the machine constants. They're based mostly by putting the spring constant is found by just not putting a specimen in there and running the indenter up and down in free space. And that knowing the force displacement relationship, you get the spring constant. The mass and the damping are found by putting the thing into oscillation and running it through a frequency sweep and then modeling this thing as a simple harmonic oscillator and figuring out what the mass and the damping are from that.
But these calibration parameters are not changing based on the, because machine parameters could be non-linear depending on the specimen.
The machine, where we're trying to separate out the machine parameters from the specimen parameters. And the machine parameters will depend on things like the position of where the indenter is. But they don't depend, the machine parameters, if this is a single degree of freedom harmonic oscillator, then all you end up with then is an extra component that comes on top of this, which becomes the stiffness and damping of the contact, which is then modeled in a model that I had back in one of the previous slides. So it's this model right here is assuming what one of those is the contact and the rest is the machine.
But those machine parameters are constant.
Those parameters in this model are assumed to be constant, and this thing works well when you do this right.
And you never get a singularity? I mean, S can be infinite.
Singularity in what?
S can be infinite in your formula.
The stiffness of the contact?
No, yes.
Stiffness of the contact could be infinite, but
Or even negative.
yeah, and we're assuming no adhesion here, okay? When we do this, so that's out of the picture. S is not infinite in real materials. It's the stiffness of the contact is 2 e sub a times the square 2 over pi.
The S is something, one thing minus another thing to the minus 1. And so before you do the minus 1, the whole thing could be 0.
The whole thing could be 0, and that's the point that I was trying to make, that unless you've got the machine very well calibrated, that you may be subtracting 1.001 from 1, and all you've got left in terms of significant digits is the 0.001. So that's the message I'm trying to get through here. You have to be careful about those things. Okay. So there's what you've got. So now where does that become important? It becomes important obviously in the measurement of viscoelastic parameters. But there's some other places where this becomes extremely important. And one of those is in what we call continuous property measurement. So remember, the basic method for measuring hardness and elastic modulus that I talked about yesterday is based on loading something up and then unloading. And it is the unloading stiffness that you're getting at the maximum load and the maximum depth of penetration where you're making the measurement. So it only corresponds to one place on that curve and one depth of penetration. Now when you use this continuous stiffness, so on this plot I'm measuring modulus, and that red data point over there for fused silica here is the one that comes from making the unloading stiffness measurement. Essentially what you're doing with this continuous stiffness thing is if you've got this thing on at a relatively high frequency, relatively high to the time period you're doing the test, then you're getting a series of unloadings from the downward oscillations, one way to think about it. And so you can get those things at the rate of 45 hertz or something or other. So in 1 second you're getting 45 measurements of what the unloading slope is. And so from that information you can measure the stiffness essentially continuously as you're going up. And so that then allows you to measure parameters like modulus or hardness as a function of depth without unloading. You're getting this information continuously as you're pushing this indenter in deeper and deeper and deeper. And that becomes a very valuable thing to have. You don't have to do thousands of experiments to figure out what depth dependencies are.
Is it at the same location? Like indenting the same?
Yeah, so at this point you're driving the indenter in at one location with this very small oscillation on top of it. So it's all at that one location. Yeah.
It's constant, yeah? So there's no compaction of material.
And this particular one, which does compact a little bit, but not much, it is constant. And actually this is a little bit of a cheat because this is a material on which we do a calibration procedure. And one of the calibration procedures basically assures that this ends up being flat. So the real way to present this would be to calibrate it on fused silica and then take a measurement on another material and then assure that that other one is in fact flat. And I could do that. I just don't have that data in this particular set of slides. Okay. Now, where does that become useful? Well, here's a good example of it. So this is now measuring the elastic modulus as a function of depth with continuous stiffness measurement for a 1,200 nanometers of a polymer, so there's your soft stuff, sitting on top of a hard piece of silicon. Okay? And the polymer has a modulus, which is probably down here at about 3 gigapascals, so it's sort of typical polymeric kind of material. And if you use the normal procedures then to determine what that modulus is as a function of depth, it looks like it's constant down here, then it's going up and up and up and up, and by the time you get to about 500 nanometers here, you're really starting to feel the effects of this stiff silicon substrate creeping in. And if you drove this all the way through the polymer deep into the substrate, this thing would eventually saturate over here at a number that goes to whatever the modulus of the substrate is. So you're getting this information continuously as you go through here. Now to further illustrate that, this is then data done with the polymer on there. That's the stuff in red. The stuff in blue is when you come in on top of this thing and you put 100 nanometers of a hard coating on top of the polymer. So this is a silicon oxynitride glass that goes on top of this. That's 100 nanometers thick. You go back and make the same measurement using the same techniques. Now you see this. This thing really has a high modulus. It's swinging down to this 100 nanometer mark, which is where you're starting to cut through that hard film. And then as you go on through, then you see that you start to approach, to asymptotically go to whatever the polymer on the silicon substrate is doing. So this technique gives you the ability to go in and
Is this a confined sample? I mean, why doesn't, I always think about if you have something stiff on top of something soft, that you just push the stiff thing down into the soft thing. So why does it actually do this?
So you got to remember that this thing that you're pushing down in is not a sphere. This thing that you're pushing down in is a sharp pyramid, and that sharp pyramiding is actually cutting through.
So you're cutting through.
You're cutting through this thing.
Okay.
Okay, and you're pushing stuff aside. Is what's going on here. Yeah.
Is there a way to dissect the elasticity of unknown sample, this technique of multi-layer sample?
You mean, could I, for example, determine the elastic modulus of the film on top up here?
Composite multi-layer sample,
Yep.
this is the thickness and give me.
So that's one of the standard problems in nano-indentation, how you do that. And there's a lot of work out there, and there are various techniques for doing this. It would be very difficult on this 100 nanometer Cylon film that's on there. Not Cylon, but silicon oxynitride, because it is so thin, and you're not getting anywhere near a plateau. But if you go back one slide and look, whoops. If you go back one slide and look at what happened before we put it on there, then that's 1,200 nanometers. And this data that we're getting down in here is going essentially to the properties of the film. Now, you may say, well, how do we get, then if it's 100 nanometers, how do we get it? How do we get the properties of the film? And the answer there is you've got to have good models for the interaction between the film and the substrate, and take data that might look like this but may not go asymptotic on you, and be able to extrapolate it back to zero depth. And there are lots of things in the literature for how you do that. That kind of answering the question? Good. I thought this stuff might be interesting.
So would 18 gigapascals be the actual property of S?
This one? No, because you haven't. In order for me to be convinced that 18 is the number up there, I'd have to see this thing plateauing out at some value, and then we didn't get there. Okay, so that was too thin to measure. Okay, now The other thing you can then do with this technique is you can measure viscoelastic properties. And you do that in different ways. This is some work done by Eric Herbert in his PhD dissertation with us. What he's done here is to look at polyvinyl chloride, highly plasticized. One thing that we did in this work was we did it with a flat punch indenter. So this is an indenter that you don't often use in nano-indentation work because you've got issues with aligning the flat punch with the surface. But in some of these softer polymers, you can actually just push them in a little bit to get it well seated. And once it is well seated, then you have the nice feature here that you know what the contact area is. There's no changing contact area. And so we were interested in just whether we could simplify the problem as much as possible and make good measurements. And we then did, we took this PVC, we did DMA experiments on macro specimens of it as a function of frequency, and there's the DMA results. We then did nano-indentation experiments using the procedures that I outlined a little while ago, and you can see that at least storage modulus-wise, things are matching up pretty well if you've got a flat punch where you know the contact area. And here's the tan delta, so this is basically the loss modulus, and you can see that it is in fact lining up pretty well here too. Notice that there's one funky data point out here, and when we saw that, we first thought, well, we're doing something wrong in the nano-indentation procedures. Later on, we went back to analyze that and found out that in the DMA, there was a resonance in the DMA testing machine at that particular frequency, and that was giving us bad results from the DMA. It wasn't the nano-indentation, it was the DMA that was giving us the bad results. So, boy, I'm going on a whole half hour with this stuff, aren't I? So here's, being from Tennessee, we're fascinated with Dolly Parton and moonshine and NASCAR racing, right? So one application for this stuff then, we were actually approached by a group at Goodyear that make tires for NASCAR. They make very high performance tires for NASCAR. And those things have multiple plies and things on them, and each one of those plies has a different set of viscoelastic properties to control their performance. And so we went in with this technique and measured storage modulus and loss modulus as you go across this thing, and you can see that some of these regions are extremely elastic, and some of these regions show less elasticity, and there's all kinds of stuff that goes on in there in designing these tires for very high performance in NASCAR. Now, I got 5 minutes left. I'm out of time. What I was going to do here today was to talk about some case studies in nano-indentation. Let me go through a few of these. So, well, let me say here that case studies is the wrong word. Okay, these are examples. And these are examples that I've come across in the 30 years that I've been doing this, of things that are kind of interesting. And sort of getting on in my career, I'm now asked to go back and give retrospective talks quite a bit. And in the last 5 years, I've given a number of retrospectives. And the theme in the retrospective has always been the same, which was, what were we trying to do early on in the days of nano-indentation that we could anticipate versus what happened with nano-indentation that we didn't anticipate, okay? And this talk is mostly about the things that we didn't anticipate, and it's sort of interesting examples of some things that happened. Now, the ones that I've picked out for today mostly come from the bio-soft materials world. I've got an equal number from the hard materials world. But let me run through a couple of these just to sort of give you an idea and a flavor for some of these things. Some of these are my own work, and a lot of them are other people's work that I've just pulled out of the literature. Now, we've seen a lot at this meeting about testing bone, and it was that relationship that I had with Jay Rowe that I mentioned yesterday that got me into this back in the mid-90s. And one of the things that we did there that has since become an extremely highly cited piece of work is, and this is one that I didn't have any idea would ever be important in the nano indentation world, was to answer an important question to the people doing bone mechanics. And that was that in bone, you've got the dense cortical bone, and then you've got the spongy cancellous bone out here on the end. And Mother Nature has obviously made one of those dense and one of them spongy for a reason, and it has to do ultimately with what the compliance of the local compliance of the bone is. And a question that was asked by a lot of the bone mechanics folks was, are the inherent properties, mechanical properties of the spongy stuff the same as the inherent mechanical properties of the dense stuff? Which is basically equivalent to saying, is the spongy stuff spongy just because of its geometric structure, or is the spongy stuff spongy because there's something different about the bone itself? And so nanoindentation ends up being an important tool to investigate that problem. What we did was to go into these trabecular struts, and you can take individual struts and mount them, and you can do indentations in the struts, and you can compare those to what you get in the dense cortical bone from the other material. And when you do that, the answer is shown here, that the trabecular bone, as we measured it in these struts, has a modulus of about 17.2. The cortical bone is anisotropic. Transversely, it's about 15. Longitudinally, it's about 21. So in the end, the answer is that the average of those is pretty close to what happens in the trabecular bone. And so the trabecular bone, the inherent mechanical properties are the same as cortical bone.
It's amazing.
So and that paper has become paper has become extremely highly cited. So that was something that I had no idea was going to happen. Teeth. So some interesting work on teeth. I didn't do this, but this is a really cool paper that if you ever want to go look at something cool. This is some work done by Tim Weiss at Johns Hopkins. This was in the old days before we had nano-indenters that didn't do things fast. And they took a section of a tooth and they made 2,500 indents on it. Some graduate student did this. Some graduate students made 2,500 indents, with each indent probably taking about 5 minutes.
And piece the arrays together, because I've done this and it's hard.
It's hard.
Back in those days.
Yeah, in those days. Now it's easy.
Yes.
Now it's easy. Now we can do this experiment in an hour. But that poor graduate student probably took days. So what they then did was then just simply go through. They had enough indents to where they could map what the local properties are, the hardness and the modulus properties. And so what you find out here is really kind of interesting. If you look at the hardness is high here, which is, the biting surface. You would expect it to be hard. But it's relatively low here. And one of the reasons it's low here is that the modulus is low there. But of course, the modulus is low there with a very important reason, and that is that's the place where the biggest bending stresses are going to be applied. And therefore, you want something with a lower modulus that's a little bit more compliant, so that it's not hard and brittle. It's really more. It's not brittle. It's not as brittle, and it is in fact more compliant. So Mother Nature's done some very interesting things with teeth here. How much longer? 5 minutes? Okay, we got better ones than this as we go along.
What's the age of this teeth, and does it change over time? Like, is your paper tracking?
What's the age of this tooth?
Yeah.
I don't have a clue.
It was an adult.
So
it was an adult, I think, primary molar, if I remember.
Yeah, it's definitely a molar. I mean, it's not like somebody sacrificed a tooth. This was a tooth that that they were going to lose. It was a boxer or something. That it was a tooth they were going to lose. If you find the paper, you can find all the details. Whether things change with age, I have never seen those studies because I just don't follow this work that closely. But just some cool pictures of things that I never expected were going to happen. Hardening of the arteries. People have gone in. Hardening of the arteries is because there's stuff in the arteries that gets hard, right? And it's this calcified tissue that forms in the plaque. People have gone in. This is a paper that Don Ebenstein and Lisa Pruitt put out a few years ago, where they took arteries in various conditions and opened them up, found the plaques, and went in and made a series of indentations in the plaque to show what happens to the hardness and the modulus as time progresses. So, and these things get pretty ugly as they go along, and the things get harder and harder and stiffer as you move on through these things.
In vivo work?
Pardon?
Is there any in vivo work doing this?
On hardening of the arteries?
Yeah.
No, but there's in vivo work on bone. Okay, I'll show that here in a second.
So this,
If there is in vivo work, I'm not aware of it. This was basically taking cadavers and splitting arteries open, and they're human arteries, by the way. So this is one we saw a little bit about yesterday. So here's an in vivo one. So this is called
Reference point.
RPI, reference point indentation. So this is a device. This is a torture device, by the way. Okay, this is a torture device. So somebody was asking about this yesterday. So here's the end of this thing. Looks like this. And that's something then that's sharp enough. It's basically a syringe needle that you can stick through the skin to get to the bone in your femur. This is a device to test bone quality, supposedly. So you've got to get through the skin and through the muscle, down to the bone. So you do it with that thing. And then on the inside of that thing, there's an indenter. And so once you get it in, then the tongue comes out and it starts to make indents on the bone. So you push that dude down in there and you start to, so it's like this. There it is. You get it in. This is then the reference probe, which is why it's called reference point indentation. It then goes and starts to push in, and all this junk back here is basically a nano indenter that's controlling and measuring the forces and the displacements as you push that dude in and you push it into the bone. And the idea is to in situ, in vivo, measure bone quality. And so here's sort of the controversy, is it's not really understood what this means. But here's the experiment that they put out to show that, in fact, it's measuring something. And what they did was they went down to the local butcher and got a steak, and they cut the bone out of it. And they then tested the bone, force displacement, doing nano indentation on it in the unbaked condition. Then they barbecued and took the same bone, and they looked. And you can see that there's clearly a difference in the response of that thing. Now, somehow that then correlates with bone quality, and as was being said yesterday, there's a company, it's this guy's company, that's now making a whole lot of money on these things as diagnostic tools. Now, I'm running out of time here, so we saw this stuff this morning about tree cell walls, so lots of really interesting stuff that's going on there, doing indentation of tree cell walls. Here's a good one. This comes from Derek Rabba, who's a metallurgist, by the way, at Max Planck in Dusseldorf. He's interested in understanding the properties of the shells of these kinds of creatures to do some sort of just what's going on, what has Mother Nature done to make these things interesting. And indentation has turned out to be a good way to probe the properties. He is a very popular speaker at Gordon conferences. And that's because he usually gives the Thursday night talk after you've had a nice dinner of lobster. I'm not kidding on that either. And that's true. Here's an interesting one I won't go into detail on, where some MIT folks have looked at this unique armor, done finite element techniques based on nano indentation measurements of the layers in the armor to figure out what the strength of the stuff is. Things that were sort of, I think, implied at this meeting. There are folks doing nano indentation of cancer cells. And this is very controversial, as I understand, as to what it means. This is one that I never expected. This particular work, what they've done is to take lots of normal tissue and then cancerous tissue, and they've identified which cells are normal and which cells are cancerous, and they've measured the stiffness with nano and AFM-based nano indenters. And in this particular case, it turns out that the cancerous tissue appears to have a lower modulus than the non-cancerous tissue. And I know it's controversial as to which way it goes, but there are people doing these kinds of things. Nano imprinting and polymers, another interesting one. This one's good. Anybody know what RDX is? Talking about plastics here. This is plastic explosive. People doing nano indentation on plastic explosive. Now, you want to be the graduate student doing that? No. Turns out that if the particles of plastic explosive are small enough, they don't explode. At least that's what that graduate student found out. I don't know about the previous ones, but that one found out that they don't explode. And there's some physical reason for that. But believe it or not, the Army and the military wants to know the elastic and plastic properties of the particles in plastic explosive, because how you make a shape charge do its job best depends on how waves propagate through this stuff. And so you need to know hardness and modulus. And so there's been studies done of that to get the basic mechanical properties of plastic explosive by doing nano indentation. Nanopulling, you can pull on things too. I'm about done. This is some work that we did looking at a 400 nanometer diameter moly fiber. If all you do in pulling is take your nano indenter and turn it around, just reverse the currents in the coils, and things pull rather than push. And if you got ways to mount these things up, you can do little tensile tests, which we've done there. A lot of folks are using these ideas to look at spider silk strength. So a lot of very interesting stuff that goes on in spider silks. Very, very interesting material with nano indentation technology in reverse being applied to that. Some of these spider silks get pretty strong. That particular spider catches and eats birds. Don't want to go to, anybody want to go to Queensland now? Big spiders there. And then lastly, my favorite example of all, and then I'll quit, which is this one right here. So this is Sarah Herbert. This is Eric Herbert's daughter. Now, Sarah was in the 8th grade when she did that. She's a senior this year, so this was about 4 years ago. And she was fortunate that she had access to her father's nanotensile testing outfit. And she did a science fair project that was entitled Marketing Hype, Fact or Fiction. Okay? And what led to this was that her mother bought her a new shampoo one day. And on the bottom, and this shampoo, I'm not going to tell you who the manufacturer of the shampoo is, because I'll get in trouble. There will be lawsuits. They'll be after me, even though I don't have deep pockets. But on the bottle of shampoo was the following statement: introducing formulas so gentle yet so strengthening. This shampoo strengthens the hair fiber after just one use, helping it resist breakage. Okay? So this becomes, if you've got access to a nanotensile tester, then this becomes the ideal science fair project. She also has, nice hair for doing this with. So she took several, so she was very statistical in this. She took several hairs out, and she set those aside as her what do we call them? The controls. And then she washed her hair. And she let it dry, and she took out another 5 hairs. And she then took them in to the tensile tester and tested. Anybody got any guesses as to what happened? So here's one of her hairs mounted for tensile testing in our machine. And you can see the hair right there. And this is just a nano indenter turned around to pull rather than to push. And here are the results. So here's the stress strain curves for Sarah Herbert's hair. The black ones are before washing with the shampoo. And the red ones are after washing with the shampoo. So I will not make a comment about the effectiveness of the shampoo or the effectiveness of the comment on the bottle. I'll let you draw your own conclusions from that as to whether or not the shampoo was, in fact, effective in doing what it said it did.
Did it have formaldehyde in it?
I don't have a clue, and I can't tell you what it is. So anyway, if you're interested in learning some more about this, Warren Oliver and I had the opportunity a few years ago to sort of put this stuff together. And there's an old, now what's turning into an old MRS Bulletin article in which much of the stuff that I've talked about here today is summarized. And with that, I will call it quits. Sorry for going too long. That's fine. That's fine.
So with the continuous stiffness measurement, you have the load, then you have the sinusoidal load.
Yeah.
Do you use the average load or the load plus the amplitude?
Well, it's interesting because for a long time, we were using the average load and didn't realize we were making a mistake because in certain materials, the assumption was always the amplitude small enough to where it's negligible. But it turns out that in certain materials, that's not a good assumption anymore. And so since that was discovered about 5 years or so ago, the software in all of the machines that we use have been changed to where it is the load plus the amplitude that is used as what the magnitude of the local peak load is.
That's for all materials or just for some materials?
We do it for all materials. And then it's just a matter of whether it makes a big difference or not.
Yeah. So I find for like,
And it's important.
I find for polymers, the average seems to look better, but for harder materials, it's the...
Okay, well, the work that we were doing was on the harder materials.
Okay.
So I haven't explored that explicitly in polymers.
Okay.
My guess is in polymers probably not too important because you're getting because the unloading curve is, because you're lower compliance and the unloading curve is not so vertical. It's the verticality of the unloading curve that gets you in trouble.
Yeah. I find it is more important in polymers, but...
Okay.
But I'm not sure why. That's what I was asking if there's a reason why or not.
One back here.
What are the application of the tissue spider, like line?
What are the applications? I don't know if there are any applications per se. There's probably some other people in here that know more about this than me. I think it's more scientific. They're trying to figure out what the spider's doing and what the structure of this spider silk is that makes it so remarkable.
I think I could add to that it's stronger than steel per weight. So if you want to have materials that are lightweight and strong, this is
I heard about bulletproof.
Yeah, I mean, so many of the ideas that go into making the very high strength fibers are they're trying to figure out how Mother Nature does it to see if they can make those even better. Is what's going on.
Is this the Mithra from the Lord of the Rings?
Yeah. Yeah. Yeah.
So maybe just to add in anticipation for the discussion at the end, could you comment what's the future?
Well, we talked a little bit about this yesterday, didn't we? I mean, for me, I know that actually there are two things for me that are the immediate future. Before I say that, let me say this. I think a lot of the future is probably in biological kind of stuff. It's in taking these tools, the kinds of things that we're seeing around here today. It's taking these tools and applying, tools that are measuring force and displacement at small scales, whether it be in indentation or compression or tension or whatever you're doing. Those kinds of tools in the biology world, I think, are going to be, there's an important future direction there. For me, back in the metallurgy and ceramics fields, the future for me right now is going to high temperatures. It's going to low temperatures. The future for me, another thing that I didn't say yesterday in our discussion was that a lot of these things that have been sort of semi-discussed here about doing things that allow you to do things in situ as you watch what's going on, or you have other techniques that can characterize, Raman spectroscopy and that kind of stuff. Those kinds of things, I think, are also a big part of the future. I have two big projects underway right now. One is to go to high temperatures and low temperatures in vacuum at very fast speeds with new ways of measuring displacements, and we're working on that earnestly right now. The other for me is building in situ systems to work in a dual beam fib, focused ion beam system, that let us go in and test things and manipulate things that are sub-micron in dimension, pick them up, mount them, test them, push on them, pull on them, bend them, make objects that have small cracks in them, but do it all inside of a dual beam fib, where the fib becomes your eyes and the fib becomes your hands because you've got nano manipulators in there to pick things up. and the fib becomes, and then the nano indentation equipment is added on inside there to measure the forces and displacements with the requisite resolution as you're doing the test.
What temperature are you looking at?
In our project, we are shooting for 1100 C right now.
Inside the field?
No, not inside the FIP. That will be in its own special environmental chamber that will normally operate at high vacuum, not ultra high vacuum, but normally at high vacuum with the ability to backfill with any gas that we might want to do.
Since we're talking about temperature, I might add, and we're talking about biology, you should try to do these tests at body temperature, which means you have to heat the stage.
Yeah, and sometimes those, 30, 40 degrees, those are the hard ones to do in terms of controlling things well.
And probably in liquids too.
Doing things in liquids is extremely important. We've heard a lot about that at this meeting. I've done some of I've got a bone project right now where we're trying to measure the viscoelastic properties of bone directly using oscillating techniques, the kind of thing I talked about here. We're doing those in liquids, in PBS and things like that. And we're doing them dry to try to figure out what's going on. And that ends up being very challenging work. And the big issue is the scatter in the data. And I think Virginia talked a little bit about that. Part of the scatter in that data is undoubtedly the inhomogeneity in the bone structure. Part of that scatter in the data, though, is surface roughness, surface pits and holes and things that you fall into, and you don't know that it's happened to you, and it's rough, so to speak.
So going back to Ivana's question about the future. So even with the simplest case of the flat surface, solid material, hard material, you need a model for nanoindentation to interpret the results. Going to the soft materials with heterogeneity and all those things, one has to rely on some model which represents the physics. And of course not the model that was used for hard solid material. Given these complexities, do you think nanoindentation is the right approach?
Well, I mean, a good example there, I think, is what was shown, about thinking of cells as being spheroids or oblate spheroids or what have you, and so there's a totally different kind of contact body there. And then the question is, how are you going to contact it? Are you going to do it with a pointy indenter? Are you going to do it with a flat indenter? What are you going to do? And then it's just a matter of geometrically modeling that contact event in a reasonable way and using the system not so much as an indenter, but just something that can push or pull and measure forces and displacements. And then you have to take, it's up to the model as to what goes on there. If you want to start with a water balloon and think about how a water balloon deforms, then you're going to learn some things about the water balloon, right? So it's really the future is in using these things to measure forces and displacements at the scales that are commensurate with the mechanical events that are important in them, and then figuring out how to do the physics from there. Okay.